Welcome to Mythosium, the channel where science meets clarity. Here, we take the most fascinating discoveries in physics, chemistry, and engineering, and explain them in plain language that anyone can understand. Complex ideas don't have to be complicated, they just need to be told the right way. Today, we're exploring one of the strangest materials ever invented, aerogel. Imagine holding a solid that looks like a puff of frozen smoke. It's so light that a small piece weighs just over a gram, only a few times heavier than air. Aerogel is sometimes called solid air, because it's made up of about 99.8% empty space. In fact, some types are so light that if you removed all the air inside them, they would actually be less dense than air itself. But what exactly is this material? How was it created? What makes it such an incredible insulator? And why has it become so important in science and space exploration? Let's start from the beginning. The story of aerogel begins in the early 20th century with a simple question. Is it possible to remove the liquid from a gel without collapsing its structure? A gel, like the jelly in your refrigerator, is a mixture of solid and liquid. It's mostly liquid, trapped inside a delicate solid network that gives it shape. The challenge is that when you dry a gel, the liquid inside evaporates, and as it leaves, it pulls on the solid framework, crushing it like a sponge. What you're left with is a shriveled, dense lump instead of a light, airy solid. The key to solving this problem lies in something called supercritical drying. Instead of evaporating the liquid, you replace it with another substance that can become a supercritical fluid. A supercritical fluid is a special state of matter where the liquid and gas phases merge together. In this state, there's no surface tension, meaning the fluid can be removed without pulling or shrinking the structure. The process works like this. First, the liquid inside the gel is replaced with something like alcohol or liquid carbon dioxide. Then, the gel is placed inside a high-pressure chamber and heated until the liquid reaches its critical point. At that temperature and pressure, it becomes supercritical, neither purely liquid nor gas. When the chamber is carefully depressurized, the fluid escapes gently, leaving behind only the solid framework. The result is a material that retains its original shape, but is now filled entirely with air. That material is aerogel. From the outside, aerogel looks almost unreal. On a white background, it's nearly invisible, but place it over something dark and you'll notice a faint bluish glow. That soft blue color appears for the same reason the sky is blue. It's caused by Rayleigh scattering. Inside the aerogel are countless nanoscopic pores, each smaller than the wavelength of visible light. These tiny structures scatter shorter wavelengths, like blue, much more than longer ones like red. So when light passes through, the blue light is scattered away, and the remaining colors that reach your eyes are yellows and oranges. It's almost like holding a miniature sunset in your hand. But aerogel isn't just beautiful, it's also one of the best insulators ever created. At first, that might seem odd. After all, aerogel is mostly air, and air isn't a great conductor of heat. But aerogel outperforms even air as an insulator because of the size of its pores. The gaps inside are smaller than the average distance air molecules travel before colliding with something, a value called the mean free path. That means heat can't move easily through the material. Hot air molecules below the aerogel struggle to bump into cooler ones above it, which stops heat from spreading. This effect is known as the Knudsen effect, and it's what gives aerogel its almost magical ability to block heat transfer. In simple terms, heat gets trapped on one side, even if that side is hundreds of degrees hotter. Experiments show just how powerful this is. When placed above a flame that reaches more than 600 degrees Celsius, the underside of aerogel glows red hot, yet the top stays cool enough to touch. You could balance a small piece of chocolate on top, and while the air beneath it burns, the chocolate would barely melt. That's the power of aerogel. Because of its incredible insulating properties, NASA has used aerogel on several Mars missions. Aerogel keeps the warmth in while adding almost no weight. The rovers Sojourner, Spirit, Opportunity, and Curiosity were all equipped with aerogel panels to protect their delicate electronics from freezing during the Martian night, where temperatures can plunge below -100 degrees Celsius. NASA also used aerogel for something even more extraordinary, capturing particles from space. During the Stardust mission, a spacecraft flew through the tail of a comet to collect tiny dust grains, traveling at nearly 6 kilometers per second. If these particles hit a solid surface, they would instantly vaporize. But aerogel slowed them down gently. As the particles entered the soft, porous network, they carved graceful trails inside, gradually losing energy until they stopped intact. Thanks to aerogel, scientists could study pristine pieces of cosmic dust, matter older than the solar system itself. So, how is this material actually made today? Most aerogels start with a silica gel, which looks and feels like a wobbly, rubbery solid filled with liquid. Typically, it contains alcohol or another solvent trapped inside a glass-like structure made of silicon dioxide. The liquid is then replaced with liquid carbon dioxide because it's safe, non-flammable, and easy to handle under pressure. Once the gel is fully saturated with CO2, it's placed inside a sealed chamber, heated, and pressurized until the CO2 becomes supercritical. In that moment, the boundary between liquid and gas vanishes. When the pressure is slowly released, the CO2 escapes, leaving behind only the delicate silica skeleton filled with air. The result is a material that feels dry, fragile, and almost weightless, a solid that's 99% empty space. Although aerogel looks fragile, it's surprisingly strong for its weight. However, it can be brittle. Drop it or bend it too much, and it shatters like thin glass. Scientists have been working to improve this by making more elastic and flexible forms, even combining it with polymers to enhance its toughness. Originally, silica aerogels were hydrophilic, meaning they absorbed water easily. Once wet, they would collapse and lose their structure. But researchers found ways to make them hydrophobic, or water repellent, allowing them to survive in humid or damp environments. These new waterproof aerogels open the door to practical applications here on Earth, from building insulation to advanced protective clothing. The biggest challenge now is cost. Aerogel is still expensive to produce because the supercritical drying process requires special equipment and precise control. But as technology improves, prices are dropping, and larger-scale production is becoming more practical. Someday, aerogel could be used in everyday buildings as ultra-thin insulation. Imagine windows or walls that keep heat inside as efficiently as 10 times their thickness in fiberglass. In extreme environments, like polar research stations or even lunar bases, aerogel could become an essential material. It's astonishing to think that this near-miraculous substance came from one simple question about drying jelly. From that question came a solid so light it's almost invisible, so strong it protects spacecraft from freezing, and so porous it captures particles from a comet. And beyond its scientific importance, aerogel tells a deeper story, a story about curiosity, the kind of curiosity that starts with a strange question and ends up changing how we understand matter itself. Every piece of aerogel is a reminder that sometimes the boundary between air and solid isn't as rigid as we imagine. It's a place where chemistry, physics, and imagination meet, where something almost impossible becomes real. Here at Mythosium, we believe science isn't just about data or formulas. It's about the wonder of discovery. Materials like aerogel prove that even the smallest ideas can lead to extraordinary breakthroughs. So the next time you see a photograph of a blue glass-like block glowing under the light, remember, it's not magic, it's science, a delicate network of silica and air, the lightest solid in the world, and a perfect example of how humans can shape even the most intangible things into something tangible. Thanks for watching. If you enjoyed this journey into the science of aerogel and want to see more fascinating stories like this, make sure to subscribe to Mythosium. Every week, we explore the hidden physics, chemistry, and engineering behind the world's most amazing inventions. Stay curious, keep exploring, and I'll see you in the next video.